Welcome, fellow chemists, to another video on SN2 reactions, in which we will take a brief look at 4 factors which affect the process. We'll look more closely at the leaving group, the nucleophile, the solvent, and steric effects. An understanding of these factors will allow you to predict the outcome of a reaction at a glance, and that includes predicting nothing happens at all. Let's start with the leaving group. In the first video, we looked at the substitution of bromide with hydroxide. We will continue focusing on the alkyl halides, so here are the equations for the other 3. In each equation, we see that the halide has been substituted, or in other words, it has left the molecule. You may prefer a different term, but chemists have designated the species that is substituted out as, you guessed it, the leaving group. With the exception of the halide, what exactly is different from one reaction to the next? To answer that, I will bring in the relative rates of these reactions. The slowest is the reaction with fluorine, which is given a value of 1, and the others are adjusted accordingly. By this measure, the rate of the reaction with iodine is 30,000 times faster than that of fluorine. The higher the rate, the easier it is for the halide to leave, and therefore the better leaving group it is, but why is iodine the runaway winner? We can build toward an explanation if we look at the acids of these halides and then examine a statement you certainly heard in general chemistry. Strong acids are said to dissociate 100%, and for the ones on the screen this is true for 3 of them. The outlier is hydrofluoric acid, which is considered a weak acid where the dissociation is less than 100%. Now the halide ions are considered the conjugate bases of those original acids. Fluoride is a strong conjugate base because it is strong enough to reverse the reaction. The other 3 are weak conjugate bases because they aren't strong enough to reverse the reaction. It may seem like I've gone on some wild tangent, so let me bring it nearly all the way home with something you should remember even if it doesn't explain anything. Strong acids make weak conjugate bases, and in a different context, weak conjugate bases are good leaving groups. Meanwhile, the weak acids make for strong conjugate bases, which are poor leaving groups. To fully come to grips with what's happening, we must take a closer look at the theory of base behavior. According to Lewis of dot structure fame, bases donate or share electrons with another atom to form a bond. The identities of B and X are irrelevant, as it's the behavior that determines whether it is a base or not. If a base is strong, it must be very good at sharing electrons with another atom. This brings us back to fluoride, which is the strongest base of the halides. It wants to bond, so it will share its electrons with another atom. An alternative statement is if fluoride has already bonded, it will not leave to get its electrons back. We saw that fluoride is a bad leaving group, and now we know why. On the other hand, iodide is the weakest base of the halides. It doesn't want to bond, which means it won't share its electrons with another atom. The alternative is if iodide has already shared its electrons, it wants to leave in order to get its electrons back. We saw that iodide is the best leaving group of the halides, and now we know why. If you're not a fan of acid-base theory, it turns out that the basicity of these halides is linked to their size. Fluorine is the smallest halide and the radius increases up to iodine, and this is true if they're ions. In any case, the smaller the halide, the stronger the base. Regardless of which explanation you prefer, we can finally make a conclusion about the halides. Since the ranking of base strength means the leaving ability of the halides is reversed, we can conclude that the reactivity of alkyl halides in SN2 reactions is as follows. To be clear, the alkyl iodide is most reactive because the iodide is most likely halide to leave. That was a lot of information about the leaving group, so let's talk about what takes its place, the nucleophile. Both hydroxide and water can act as nucleophiles since the oxygen atoms have electrons that can be used to bond with another atom. Of the 2, hydroxide is the better nucleophile because it is the stronger base, and we know that stronger bases more effectively share their electrons with another atom. Even if the base looks more complex, or contains a different attacking atom, what we already know remains true. Stronger bases are better nucleophiles. Since each of these pairs were roughly the same size and always had the same attacking atom, the stronger base remains the better nucleophile regardless of the identity of that atom. That's worth remembering, but how do we determine the better nucleophile when there are different attacking atoms? I'll get to the different atoms in a moment, but let's start in a familiar place, base strength. Of the 3, amide is the strongest. It turns out that the nucleophilicity of these examples follows the same pattern. If you're thinking, this is too easy, stronger bases are better nucleophiles forever and always, well, I have some bad news for you, it's just not that simple. The reason this pattern holds is the relative sizes of nitrogen, oxygen, and fluorine are quite similar. They're not exactly the same, of course, but not different enough for it to be a factor. However, before this part of the video, we saw that fluoride is a better base than iodide. Using what we have covered so far, we would conclude that fluoride is the better nucleophile. But clearly, iodide is much larger than fluoride. If these two were to approach a random carbon atom from the same distance, we can see that the iodide will interact with it first. Does this mean iodide, the weaker base, can be a better nucleophile than fluoride? Yes, depending on where the reaction takes place. Reactions can occur in the gas phase, but also in plenty of solvents which might be polar or nonpolar. You might be shocked to hear this, but there are actually two types of polar solvents, protic and aprotic. Two of these situations don't require us to think that much. First is the gas phase, where we can apply the normal relationship between base strength and nucleophilicity, and second is in nonpolar solvents, where we can say the same thing. This contrasts significantly with polar protic solvents such as water, methanol, and formamide. Unlike nonpolar solvents, these have at least one hydrogen bound to oxygen or nitrogen, which results in ion-dipole interactions or intermolecular forces called hydrogen bonds. Strong bases like fluoride are strongly attracted to protic solvents, whereas weak bases like iodide are only weakly attracted. This means if fluoride encounters the intended carbon target, it can't break away from the solvent, but the iodide can break away from the solvent and stick to the carbon. We can conclude that in protic solvents, weaker bases are better nucleophiles. The final type of solvent for now is called aprotic and includes acetone, acetonitrile, and DMSO. These are capable of dissolving ionic compounds, which may be the source of the halide in the first place, and as you can see in their structures, they do not have hydrogen bound to oxygen or nitrogen, and therefore will not interact via hydrogen bonds. Without those interactions, the strongest base is once again the better nucleophile. All of that may have been quite a lot to take in, so luckily I have saved the simplest one of all for last, steric effects. These are, if you remember from the previous video, related to the size, shape, or structure of the molecule and how they influence reactivity. The examples I will use to model these effects are the rather bulky T-butoxide and much smaller ethoxide ions. For the record, T-butoxide is a stronger base and should be the better nucleophile. The analogy I will use to compare them is to think of these ions as keys and the target as a lock. With a lock that is relatively easy to access, both ions can fit without issue. However, I'm going to change the shape of these locks just a bit with these additional lines which no atoms are allowed to pass. As we can see, if both approach straight on as they did before, only ethoxide fits. T-butoxide shouldn't worry because there is no rule giving nucleophiles only one angle of approach. Rotating the ion about the oxygen atom a few degrees anti-clockwise results in an orientation where T-butoxide successfully fits. As you can see though, there is very little wiggle room, or in other words, very few angles at which it can successfully attack this target. Not only did ethoxide take its original pass, we can see there is an even wider range of orientations where it would still reach. We can take this to its natural conclusion by changing the target shape yet again. The new structure makes a reaction with a bulky nucleophile like T-butoxide improbable, if not impossible, but remains quite easy with ethoxide. There was a lot covered in this video, so I'll summarize everything, starting with steric effects, where we just saw the better nucleophiles are smaller, less hindered bases because they are more likely to actually reach their target. When we consider the conditions in which the reactions occur, the better nucleophiles in protic solvents are weaker bases because of fewer interactions with the solvent. However, the better nucleophiles in aprotic solvents or in the gas phase are stronger bases. And remember, the video started with talking about the best leaving groups, which are weaker bases because they would rather keep a pair of electrons than continuing to share them in a bond. On that note, we have reached the end of the second video on SN2 reactions, and we have covered quite a bit of what I want to. All that remains is the reversibility of the process, and then I may move into SN1 reactions or something else. Until I get to it though, thank you very much for watching this one, and if you have any comments or requests, please leave them below.